Hello and welcome to this episode of the Industrial Engineering Notebook. Today's topic is defining derivatives. This is just going to be an overview of what a derivative actually is. We won't even really get to the derivative rules, but that's okay because it is important to just understand what this is before we get into all the math. So basically, the position of something, where something is really easy to know. You can kind of just look. You can measure it, you can use a ruler, you can do whatever. A position of something is generally easy to know, or the position of the amount of money in your bank account. You just check and you can see how much money is in your account. Speed, on the other hand, is harder to know and often it's more important to know. So what is speed? Speed is just the rate of change in position. How fast is your position changing? So you can think of like a car here, or there's other kinds of speed, right? There are other kinds of change. So if there's $50 in your bank account, well, that's kind of sad, but it's an easy position to know. Really what you're more interested in is how is that amount in your bank account, how is that $50 changing? Maybe, just maybe, that is increasing by $100 a minute. Wow, then you are set, you are golden. But maybe it's only decreasing. Let's say it's decreasing by $50 a minute, and that would be very sad. Or maybe it's increasing by $1,000 a minute. So you see, just knowing the position of where you are at with your finances isn't enough. It's actually more important to know how that's changing. Is it increasing? Is it decreasing? And then how fast is it increasing or decreasing? And if you've taken algebra before, you already kind of have a way to figure out rate of change. So we have our input x and then our function f of x. And if we want to know how fast, we just take the slope. Remember, rise over run. So you're just picking 2 points on this line, and then you do rise over run. I bet that's a rise of 1 and a run of 2. So over here, I'm going to draw the derivative of this function, the rate of change. How fast is it changing? And we see here that no matter where you are, what value of x you have, the rate of change is always the same because you can just pick 2 points and you're going to get that same slope no matter which 2 points you picked. So there's the graph of the rate of change. It's 0.5, 1/2. Where things get more complicated and where calculus really comes in is when your function's not a nice easy straight line. It's something that's kind of curvy, right? So I'm drawing a parabola here. We got a nice curve. And here all of a sudden it's not so easy to do your rise over run, to pick 2 points and do rise over run. Like if we want to know the rate of change at this point, well, what's the second point that we're going to pick? I mean, we could pick this one and we could try to do rise over run there. But what if we had picked this point? Then there wouldn't be, well, then I guess, yeah, see, it's a straight line. So it's like now your slope all of a sudden is really, really hard to find. So which 2 points do we pick? And the answer is we want to pick 2 points that are right next to each other, as close as 2 points can get to each other. And we're going to draw a line between those 2 points. And this is called a tangent line. And a tangent line is nice and straight, just like from before. So we can actually just do the slope of this line instead. We don't have to worry about the rest of the curve because we just want to know the derivative, the rate of change at this point. And so then we do our rise, and then we do our run. And I don't know, that looks like a rise of 3 and a run of 2. And looking at the graph of the derivative, at the graph of the rate of change, we know that at that point, I'm guessing, let's say this is an x value of 2. So at an x value of 2, we know at that point we're going to have a slope of 1/2. Not 1/2, 1.5, my bad. So we already know 1 point on our rate of change graph. And so ultimately what we need to do is for every point, we got to take 2 little points here, draw a tangent line, and then we'll need to take 2 little points there and draw a tangent line. And the slope of these tangent lines is changing. If you pick 2 points right up here that are right next to each other, you get a flat tangent line like that. And I already happen to know what this rate of change will look like if you went through and you did all the slopes here and you plotted the points. So for a parabola like this, the rate of change would look like this. And what do we notice about these two? As f of x is increasing, f prime of x, the rate of change, is positive the whole time. It's decreasing, the rate of change is decreasing, but it's positive the whole time. And we notice here, right when we hit the peak, right when it goes from increasing to decreasing this function, the derivative goes from positive to negative. And if we were to pretend that this was f of x and we did another derivative, we'll call it f double prime of x, that means the derivative of the derivative, we get something that looks like this, just a straight line, and it'd be negative because this line is decreasing. There's a negative slope, so the derivative of the derivative would be some negative number. And there are equations, so you wouldn't have to draw the tangent line at all these points and plot your derivative and then plot your second derivative. There are equations that'll do it for you. But right now, the point is just to get an understanding of what a derivative actually is. And here's why it's important, especially in industrial engineering. If you want to maximize a curve, if you want to find the top point in a curve, you can use derivatives and some little tricky things to figure that out. So here we can identify the maximum of this function by just looking at where the derivative of the function equals 0. So to find max or min, set the derivative equal to 0. And if you want to know which one you have, this doesn't tell you if it's a max or a min, it just tells you if one of these two. It'll be a maximum if the second derivative is greater than 0 or positive, and it'll be a minimum if the second derivative is negative or less than 0. And you might wonder, okay, why go through all these extra steps to find the maximum or the minimum? It's easy to know position. Just look at the top or look at the bottom. And you're right, for an example this easy, yeah, you could just identify it and probably figure out what your x is. But as you advance in industrial engineering, you're going to get equations that are increasingly more complicated, and it won't be easy to just draw out the graph like this. We need a way to just look at the equation and just from the equation, without plotting anything, figure out where the maximum or the minimum is. In my next video on derivatives, I'll go over just that. How can we look at the equation, find the derivative, and the second derivative if we have to. And eventually I'll get into some application videos where we can see how we can maximize things like profit using derivatives. If you liked this video, please hit the like button. If you want to see more videos like this, hit the subscribe button. And if you have questions, please put them in the comments.